Okay guys, so today we're going to finish up 4.2 notes. We're going to finish what we started yesterday. So to be able to do that, I want to talk about what you came up with for your answers on last night's homework, in particular the second part of the homework. So for your left endpoint, we came up with 3.75. Then for the right endpoint, it should be 5.75. And then for the midpoint, you should have 4.625. And we talked about the fact that for this particular function, the left endpoint was an underestimate, the right endpoint was an overestimate, and then the midpoint was a better estimate than either the left or the right for this particular function on that interval. Now, for your homework, or the second part of your homework last night, I asked you to, okay, this is not my student. Okay, that's okay. So I asked you to use midpoint Riemann sum with the same function, but you were to use 8 rectangles. And if you worked out the problem correctly, what you should have come up with is 4.65625. And the way that you would do that is by taking the base times the height of each of these 8 rectangles. And the base is going to be 1/4 for each rectangle. The height is determined by the y value when x equals the midpoint of each rectangle. So the first midpoint, I used 0.125. It's the same thing as 1/8. So to find the height of the first rectangle, you would do 1/8 squared plus 1. The height of the second rectangle is 3/8 squared plus 1. The third rectangle height would be 5/8 squared plus 1, and so on. So the idea is the more rectangles you use, what? The better the estimate is, right? So if I were to ask you to use Riemann sums to approximate the area under the curve with n equals 16 rectangles, that would be a better estimate than this. With 32 rectangles would be a better estimate than this. Remember, n is the number of rectangles. What we're doing today is we're going to find the actual area under the curve, because we're going to sum n rectangles as n goes to infinity. Okay? So what you're learning today is the limit process for finding the exact area under the curve. These are all approximations, right? These are just approximating the area under the curve. The formula that I'm giving you today is the limit process for finding the area under the curve, using the idea that we are summing n rectangles as n approaches infinity. So I'm going to give you this kind of nasty formula, okay, that we're going to use to help us find the actual area under the curve. So let's jump straight into it. You can continue on your notes from yesterday if you want, or probably want to start a new page since we had guided notes yesterday. But this is still section 4.2. We're finishing it up today. And again, this is the limit process to find area under the curve. And by the way, when I say find area under the curve, what do I really mean? Between the curve and the x-axis. That's right. The limit process to find the area under the curve means what we're actually doing is finding the area between the curve and the x-axis. So here's the formula that we're going to use. There's a formula, and then we have to define some variables in that formula. So you want to have the limit as n approaches infinity of the summation from I equals 1 to n of f of c times delta x. So we're using a limit. Why do you suppose we're using summation?
Because it's
Because you want to add up all the rectangles, right?
Yeah.
You're summing all the rectangles. That's what we were doing when we were approximating here. We were adding together all the areas of each rectangle. So that's just a shorthand for adding the area of each rectangle. F of C is just the height of each rectangle. F of C gives you the height of each rectangle. And so what would delta x give you?
The width.
Yeah, the width or the base, yeah. Delta x is going to be the base. So you're summing the height times the base for all rectangles between 1 and n, where n is approaching infinity. And if you do this process using what we learned yesterday, some of the shortcut formulas that we learned yesterday, it will give you the actual area under the curve. No approximation, the actual area under the curve, which is really, really cool. We do need to define C and delta x a little bit better before we move on. For delta x, for you to compute it, you're going to do b minus a over n. Now let's talk about what b, a, and n are. Well, first of all, you know n is the number of rectangles, so we're going to use n because n is approaching infinity. What about a and b? What are those? Any ideas?
Would that be the start point and the end
Yeah,
point?
exactly.
Or the
Those are,
endpoint, start point?
yeah, those are the endpoints. We're looking at the area under the curve on a closed interval A to B. So B is the right endpoint and A is the left endpoint. So hopefully that makes sense to you if you think about the examples yesterday. A is 0, B is 2. So our delta x is 2 minus 0 over the number of rectangles. The number of rectangles was 4 in the first 3 examples. So 2 over 4 gives me 1/2. That was the base on the rectangle for the first 3 examples. And then for the last night's homework, b minus a over n was 2 minus 0 over 8, which is a fourth. And so the base of each rectangle, when we added them all together, was a fourth. So that's where delta x comes from. That's just telling you the base of each rectangle. And we're going to use b minus a over n because our n is going to infinity. We're not going to have a particular number for n. And then the other thing is c. To find c, you're going to do a plus I delta x. So the left endpoint A plus I times delta x. So what that will do is for I equals 1, it'll give you the endpoint plus the 1 width. So it'll give you the first rectangle. And then when I equals 2, it's A plus 2 delta x. So it gives you the second height, then the third height, then the fourth height, all the way up to the nth height. Okay, so that's kind of where this formula comes from, but we're going to use this formula to help us find the actual area under the curve of the problem we were looking at in class yesterday. This is so cool. You guys got to get excited.
Whoa.
Okay, here we go. So Do you guys remember what the function was yesterday? What was f of x? X squared plus 1 on what interval?
0 to 2.
0 to 2, okay, so we're gonna use f of x equals x squared plus 1 on the interval 0 to 2. And so we're gonna use our formula, limit, well actually, you know what, before we do the formula, let's go ahead and figure out what delta x and c are, and then we'll substitute those into the formula. So help me find delta x. We said from yesterday's interval, b was 2 and a was 0. So again, the definition of delta x is b minus a over n. And for this particular problem, I'm doing 2 minus 0 over n. You don't substitute in anything for n because n's going to infinity. And then 2 over n is our expression that we're going to use for delta x. Now let's figure out c. C is a plus I delta x. So what is a for our example? 0. Plus I is used in our summation. And we said delta x was 2 over n. So I'm actually going to write this, instead of 0 plus I times 2 over n, I'm going to simply write it as 2I over n. And I'm going to substitute 2I over n for c, and I'm going to substitute 2 over n for delta x into the main formula that we start with. Limit as n approaches infinity. Everybody okay so far? All right, so we should have the limit as n approaches infinity of the summation from I equals 1 to n of f of c. Now think about what it means to find f of c. You take the c value that you just came up with and you sub it in where? Into the original function, which was x squared plus 1. So instead of writing x squared plus 1, I'm going to write 2I over n squared plus 1. And I'm going to put a big old parenthesis around that. That is representative of the height of each rectangle. F of c is the height of each rectangle. Now I need to multiply the height times the base, which is delta x. And we said the expression for delta x is 2 over n. Now, if you don't have out your guided notes from yesterday, you may want to dig those out real quick, because in the next few steps, we're going to be actually using some of those formulas that we used on last night's homework. So after you get it set up, after you get this big formula set up, what you want to do is simplify it first. Simplify the expression after the summation, and then we're going to use our properties from yesterday to, the shortcut rules from yesterday, to simplify the summation before we actually take the limit. So taking the limit as n approaches infinity is going to be our last step. So we just kind of drag that piece along with us until we clean up this mess over here. So I'm going to write limit as n approaches infinity of the summation from I equals 1 to n. And inside that first parenthesis, I'm going to change it to 4i squared over n squared plus 1 times 2 over n. All I've done at this point is squared 2i over n. That's the only thing I did from step 1 to step 2. I squared my 2i over n. What do your instincts tell you to do next? Yeah, distribute the 2 over n from the right-hand side. That's exactly right. Distribute the 2 over n so that you have the limit as n approaches infinity of the summation from I equals 1 to n of 8i squared over n cubed plus 2 over n. Now that you have it simplified, think back to what we were doing yesterday. Yes,
You can take the summation of each part.
exactly, yes. You want to use the property, I think it was number 2 on yesterday's sheet, where you take the summation of each piece. And so I'm gonna start a new sheet here, but I'll leave that line up so you can see it. And so we're gonna do the limit as n approaches infinity. And then I'm just gonna put a big bracket here because the limit is gonna apply to that entire expression. And so I'm gonna take the summation from I equals 1 to n of 8 over n cubed times I squared plus the summation from I equals 1 to n of 2 over n. Now, you may be wondering why I rewrote this first fraction. But probably not if you remember the last example from yesterday's lesson. Do you guys remember why I separated it?
Because
N is just a number. That's right, n is just a number.
And if it's a number, then you can take it out.
And if it's just a number, you can pull it out front. That's great. So I went ahead and just saved myself some writing and separated it while I was distributing my summation through. And so now I can rewrite it as the limit as n approaches infinity of 8 over n cubed times the summation from I equals 1 to n of I squared plus 2 over n times n. Okay, so 2 things I did there. I pulled out my 8 over n cubed since it was a constant. And I went ahead and used my property number 3 from yesterday's lesson. Since I know 2 over n is a constant, I didn't have to pull it out in front of the summation because it was the only thing after the summation symbol. I could go ahead and use property 3, which says the summation of a constant is just that constant times the upper bound. So I changed that summation using property number 3 from yesterday's lesson. Instincts on what we should do next?
take the I squared summation.
Shortcut. Use the shortcut rule for I squared. Okay, so let's do that. Limit as n approaches infinity of 8 over n cubed. What is the shortcut rule for I squared?
N times n plus 1 times the quantity of 2n plus 1 over 6.
Good. N times n plus 1 times 2n plus 1 all over 6. Great job. And then, can I just say plus 2? Because my n's will cancel.
Yeah.
Alrighty. Any questions up to this point? Alright, let's do some simplifying inside our brackets. So if we simplify inside our brackets, I would probably first of all cancel out one of the n's. So make this denominator n squared here. And I would go ahead and probably multiply these binomials together so that we don't have to write the whole thing a million times. I'm doing a little bit of work inside the brackets before I move on. So I'm going to FOIL this together. I get 2n squared plus 3n plus 1. N times n is 2n squared. Outside I get n, inside I get 2n, so I went ahead and added them together for 3n in the middle. And then 1 times 1 gives me 1. All right, now we're ready for a new line. Limit as n approaches infinity of, distribute your 8 in the top and make it 16n squared plus 24n plus 8 all over what? 6n squared, good, plus 2. Close with a bracket. One more step of simplifying. I'm going to take that fraction and I'm going to rewrite it by dividing everything on top by 6n squared. What is 16n squared divided by 6n squared? It'd be 16 over 6, which reduces to what? 8 over 3? Yeah, 8 over 3 plus 24n over 6n squared.
So 4 over n.
4 over n, good. And then 8 over 6n squared.
4 over 3 n.
4 over 3n squared. And then plus 2. All right, now we gotta dust our brains off a little bit and think back to properties of limits. Take the limit of each one, that's right. Find the limit of each piece. And so, what is the limit of a constant? That constant, right? So the limit of 8/3 as n approaches infinity is just 8/3. What is the limit of a constant over a variable? We have a theorem for this.
Oh, it's gonna be.
Somebody whispered it. 0, yes, 0. Remember that little theorem I gave you along with the Algebra 2 rules, and I said, we'll use this again later, so you need to know it even though the Algebra 2 rules are quicker and faster. It's later. We need that theorem. We need that theorem now. So this one goes to 0. What about this one? Still goes to 0 because this is like 4/3 times 1 over n squared. So anytime you have a constant over a variable to any power and you're taking the limit as it approaches infinity, it goes to 0 according to that theorem.
Yeah, and also like the Algebra 2 rules, and if the degree of the denominator is higher than the degree of the
Yep.
numerator.
You got it. Yep. And then what about the limit of 2? It's just going to be 2. So I have 8/3 plus 0 plus 0 plus 2, which is just 8/3 plus 2. Let's write it as a fraction first. 14/3. So 14/3 is our exact area under that curve between 0 and 2. 14/3. Let's look at the decimal form of 14/3 and see how close we were with our approximations. All right, so if I do 14/3, by the way, if you're using your 89 and you type in 14 divided by 3, you want to do diamond enter to get the decimal approximation. Otherwise, it'll just spit out the fraction 14/3 at you. Okay, 4.6 repeating is the area under the curve. Let's look at our answers from yesterday and from homework last night. 3.75, we said that was an underestimate, and it is. 5.75, it's bigger than 4.6 repeating, yes? 4.625, we said that was the best estimate, and it's really close. What about last night's homework? 4.625 was with how many rectangles? Well, 4.625 was with 4, but 4.65625 was with 8. So we actually got pretty close with 8 rectangles. But the exact value is 4.6 repeating, or 14/3. Isn't that cool?
That is.
Super cool.
Now you can find the area under the curve between two values.
It's faster than it is. It's faster than it is.
Yeah, but it's not exact.
I don't care.
That's good enough.
No, it's not good enough. Calculus is so powerful, it gives you the exact answer. Okay. All right, so here's what I want to do next. I want to give you an assignment over this portion.
So excited.
So it's going to be on page 263. I want you guys to do 47 through 51 odd and number 52. Now, there's only what? 4 problems because they take a whole page, don't they? They take a long time, so there's only a few
Actually,
problems.
52 is just kind of random. Let's just take it off.
No. I want you to do all, what is it, 4? Yeah, all 4
Are you sure you
problems.
want us to do it in this order?
Are you positive?
Yes, please do it in this order. All right, so now I want you to get out homework. And I want to just use the rest of the time to answer some of your questions that you've had about homework. Now, I gave you even solutions to 4.1 already, yes? Even solutions to 4.1, you should already have those. 4.5 didn't have any even solutions. And then what about 4.2 from yesterday? Did I give you any even
Yes.
questions yesterday? Okay, I did. So let me give you those answers first. And then I'll answer any of the questions that you have over your homework so far. It could be from any section, really. So this will be sort of like a half of a homework puzzle.
Which one are we looking over?
I'm giving you answers to last night's even questions first. And then I'll just open the floor up to any homework questions you guys have over any of the sections from chapter 4 that we've been working on. Okay, so it was 4.2. You had to do number 16, I believe was your first even. So the answer to number 16 was, you tell me. 195, good. 16 was 195. Anybody get 18? 375, great. Number 20. 3,080. 3,080 for number 20, good. 36, let's see. Now 36, you have multiple parts, right? You had to find S of 10, S of 1,000, S of 100, S of 1,000, and then S of 10,000. So your answer should have been 2.5, 2.05, 2.005, and then 2.0005. Those were your answers for 36. And then you also had to do 38 for me, same deal. After you came up with your equation, you just had to sub in those numbers. So 1.056, 1.006566. You ready for 1,000? 1.00665667. 7. And then finally, 10,000 was 1.000066657. Stay away from 10,000.
Y'all can't explain complete that problem.
Okay. Those should have been all your even. Now you should have all the even problems. So let me see if you guys have questions over, again, it can be any of the chapter 4 homework. Yes, ma'am.
On section 4.5.
Yes.
It was 21 and 22.
Okay, section 4.5. So if anybody needs section 4.5, just kind of follow along with us here. So 4.5, we'll start with 21,
Yeah.
okay? All right. So 21 on 4.5. It says, find the indefinite integral and check the result by differentiation. So we are taking the integral of x squared over 1 plus x cubed quantity squared, and that's dx. So right away, I know that I'm gonna have to use u substitution here. Before I use u substitution, let's go ahead and rewrite it so that it's no longer a fraction. So I'm gonna rewrite it as 1 plus x cubed to the negative 2 times x squared dx. And I wrote it like this, just anticipating the next step. Because in my head, I know what my u is going to be, I know what my du is going to be. And so that's just saving me some writing, going ahead and setting it up that way. What is u for this example?
1 plus x.
Good, 1 plus x cubed, which means du is
3x squared.
3x squared dx. Good, 3x squared dx. So I have the u, I have the x squared dx, but I'm missing a 3. Is everybody okay if I put a 3 in here and balance it out with my 1/3 out front? Instead of putting it in there and pulling it out. Everybody okay with that step? Okay, so if you add in a 3, you do have to balance it out with its reciprocal 1/3, but then you also use your property which says pull the constant out in front of the integral sign, the constant that we don't need. We do need the 3 in there though, because we want to change 3x squared delta x to du. And so now I have 1/3 times the integral of u to the negative 2 power du. And so I bring down my 1/3. And I'm going to add 1 to my exponent, divide by my new exponent. So negative 2 plus 1 is negative 1 over negative 1 plus c. And so I can rewrite that as 1/3 times negative 1 over u plus c. Because I can do positive divided by negative makes the whole thing negative. U to the negative 1 goes to the bottom and becomes u to the positive 1. And so now, 1/3 times the negative u is negative 1 over 3 times u. But instead of writing u, I'm going to write my 1 plus x cubed. And then plus c. Does that make sense, Angel? Good. Yes.
Can we do number 11 in the same section?
Sure. So x cubed times x to the 4th plus 3 squared. So this is still in 4.5. and we're doing number 11. X cubed times x to the 4th plus 3 quantity squared. And we're taking the integral with respect to x. So I'm gonna let my u be x to the 4th plus 3, and my du is gonna be 4x cubed dx. And so when I rewrite it, I see that I'm missing a 4, so I'm gonna move my x cubed down with my dx. I'm missing a 4, so I'm gonna balance it out with a 1/4 out front. And then I can change it to 1/4 integral of u squared du. And so now when I add 1 to the exponent and divide by the new exponent, I have u cubed over 3 plus c. And that gives me u cubed over 12 plus c. Okay so far? Okay. And then the only other thing I'm going to do is I'm going to put my x to the 4th plus 3 back in the place of my u and divide it by 12 plus c. And you may even write it, I'm not sure, I didn't look at that one in the back, but they may even make it 1/12 times the quantity x to the 4th plus 3
That's
cubed.
what it said in the back.
That's another way to write it. Instead of dividing that parenthesis by 12, you can just multiply it by 1/12. Either way though, I like it like this, but you're going to be able to recognize it either way. Oh, you know what I do want to do is give you answers to the worksheet, yes. In particular, the word problems on the worksheet. I want to look at those real quick. If you have your worksheet with you, go ahead and get that out.
You're talking about the group one, right?
Yeah, the group worksheet. All right, so let me give you answers, and then if you need any of them explained, I'd be happy to do that. If you start on the handwritten side, because I know there were a lot of people in this class out that day for the PSAT, excuse me. On the front handwritten side, number 1 should be 1/2 x to the 4th plus 4/3 x cubed minus 1/2 x squared plus 7x plus c. Number 2 is 1/10 x to the 5th plus 2/9 x to the 3rd minus x plus c. Number 3 is 3 sine of x plus cosine of x plus c. Number 4 was the one that you do not know how to take the antiderivative yet.